This board, these 4 sessions, we will finish off section 3. There are 4 sections in the chapter, and this one is finishing off regular languages, and then the next session, session 2, we'll start on section 4, which is on non-regular languages. In other words, they're a category of languages that cannot be recognized by finite automata. So be talking about that for the next half a dozen pages or so, and then that will take us to the end of the chapter. And then the next chapter is quite a bit shorter, I think. Like this one's been about one of the longest, about 50 pages. I've never had so many video clips for one chapter before. I'm over 100. So it's this book's going to take me about 3 months to get through at the rate I'm going. So it's not too often I'll take a 400-page textbook. But I've chosen this one because I won't be giving many courses on computer theory, on computer science, because my main thrust is pure math and math physics. But since one of the goals in teaching all this pure math and math physics is to create theoretical physicists, mathematical physicists who understand computer science, who can deal with topological quantum computing when it comes along, with all the math and physics that it needs. So these mathematical physicists will need to understand some principles of computing, computer theory. So it's mainly for that reason that they include some courses on computer theory. It's like theory of computation, theory of complexity, computability, that kind of stuff. Okay, so chapter 2 is only 101 to 130. It's only 30 pages, so quite a bit shorter. And some two or three others also around 50. So, so when we get on to complexity theory, the first chapter in complexity theory, that's part 3, is it's about 50 pages. All right. Okay, so what we're doing before we get into this next section, 1.4, on non-regular languages, we finish off section 1.3 with 2 examples of how to start with DFA, and from that create its corresponding, its equivalent, this technical word, equivalent, regular expression. Okay. Now we started doing that for the first example of 2, and the DFAs that we use are pretty simple. Like the first example, the DFA only has 2 states, and the second example only has 3. But you'll see with an accession, even with only 3 states in the DFA, the equivalent regular expression that is long. It's huge. I could almost wrap around a whole square writing it out. You'll see in the next session. Right. Now we started a bit on the first example, so example 1.66, and the task is to, you start with a DFA. Here it is here, a 2-state DFA, and you're to, from that, construct the equivalent regular expression. So you go from a DFA to a regular expression, and that's the task. And we'll do two examples of it. The second one, so example 1.68. And you may ask me, what happened to 67? I think it's one of these figures. I don't bother labeling all the figures, just the critical theorem numbers and so forth. Okay, so we got started on it, so I'll go through most of these steps fairly quickly, and the last step I don't think we did. Well, I think I did it verbally, but actually write it out. Okay, so here's your DFA that you start with. Go through, so I'll have 4 figures, so you see the steps. So figure I've just labelled A, this figure B, C, and D. And from figure to figure, what I'm doing is what's the technical term? Like I'm ripping away one state at a time. Okay? And then you rip away the state, and then you repair the damage by changing the labels on the transition arrows. Okay? Now this part here may seem familiar, and that's because I've just left it from the previous board. Okay? This part here. And I've left it for obvious reasons. I need it. It's useful. I particularly need, well, this and this to be able to modify the labels on the transition arrows after I rip out each time. After I rip out a state from the GNFA. Okay. So going from a DFA to a regular expression, 2 steps. I've done this quite a few times now. First step is you create from the DFA a GNFA. It's pretty simple process. You add. So we're going from this to this. So this is the result. This is the GNFA that results from adding an extra start state here and a single accept state. So you add 2 more states to this one, whatever this DFA is. Now this is just a 2-state DFA, so this GNFA here will be 2 plus 2, 1, 2, 2 plus 2, so a 4-state GNFA, and then with this GNFA, one by one, we rip out, we remove a state until we get to a GNFA that only has 2 states in it, and then we look at the label on the transition arrow from the start state to the accept state, and that label, that will be the regular expression, the equivalent regular expression, equivalent to this DFA that you're looking for. Okay, that will be it. Alright, so we start now with the second part of the process. First part is to construct the GNFA. Right, well, you add the start and accept states. Alright. Well, by the way, the transition arrows from the start state to the start state of the DFA is it's an epsilon transition arrow, and for each of the accept states of the DFA, you put a transition arrow to the accept state, one of them. Remember, a GNFA only has 1 accept state. Okay? So for each accept state of the DFA, and in this case there is only one, so it's this one, you put an epsilon transition arrow from the accept state of the DFA to the accept state of the GNFA. Right? That's this one. Okay? So these 2 transition arrows are epsilon arrows. That was part of the recipe, if you like. Okay, now have a look at this. So we move on one. Now what's missing? State 2. We've ripped out, removed state 2. Okay, it's not here. So now, so we update this label between 1 and A. See, this one's now ripped out. So this all gone, and all that's left is, well, you still have this transition. Now remember, convention is with these diagrams, these state diagrams for GNFAs, so as not to clutter them up. We have not put in the transition arrows whose labels are the null set. The looks like a a 0 with a stroke through it, the null set, the empty set. But they're there. They are there. We just haven't written them, drawn them. Okay. So that's now here. Here I've got in a dotted line here the transition arrow from state 1 to state A.